SHM, you say that you are related to uniform circular motion. See, I understand that both of you are periodic motions, but that guy goes in circle. You go to and fro. So how the hell? Oh, James, you've been here the whole time. So are you a victim of education system who thinks it is difficult to relate between SHM and uniform circular motion? Then worry not. This video is for you. In this video, we'll go into the details of this topic, understand every bit of it, and if that's not enough, we are also going to practice a lot of numericals which are based on this concept. So worry not, and let's begin. So let's begin with our concepts first. So the first thing that comes to my mind whenever I start to relate between uniform circular motion and your SHM is uniform circular motion or SHM? Because if you see, I said this in the beginning of the class that both of these are periodic motions, right? So is uniform circular motion SHM, and maybe that is how they are related. And the clear-cut answer to this question is no. Uniform circular motion is not SHM. Okay, if you know, for motion to be SHM, it has to satisfy some basic conditions, right? Like the force in SHM is given as minus kx, and if you see the force in uniform circular motion, okay, that will be the centripetal force. It is given as mv square by r, which is nowhere close to minus kx, right? So the force equation does not satisfy that of the SHM. Also, if you see, the acceleration in case of your SHM is given as minus omega square x, okay? And in case of your uniform circular motion, the acceleration is v square by r. Again, these two are not even close, right? So these conditions of SHM are not satisfied by your uniform circular motion, which basically means that your uniform circular motion is not SHM, and that is how they are not related. Okay, so how are these two related? That is the question we are going to answer. But before that, we are going to use this term. Okay, so keep this term in mind. It is projection. Okay, projection. Now there is a nice scientific definition for this term, but we won't go into this. Okay. Now whenever I say projection in today's class, you are just supposed to picture it this way. Okay. By projection, I just mean shadow. Okay. Projection means shadow. There is one condition, that the light should be shine perpendicular to the screen. Suppose I tell you to get the projection of this object. Okay, so you take the object over here, you shine light perpendicular to the screen. This is the screen, this is your object. You shine light perpendicular to the screen. Okay, so whatever shadow that you get is nothing but the projection of that object. Okay, now if this object is moving, the projection, the shadow will also be moving. Okay, so projection in a lame way just means that it's just a shadow of that thing. Okay, so why did I mention this term? Okay, you'll come to know. What we are going to do is that we are going to watch the shadow of an object which is performing uniform circular motion. Okay, an object which is performing uniform circular motion, we are going to shine light on it and see what is the shadow of that object doing. Okay, and you are going to note an amazing thing over here. Okay, so let's consider an object over here which is performing uniform circular motion. Okay, suppose in the clockwise direction. Okay, so this is a particle. Okay, so after suppose some time t, so let's take the first projection. Okay, at time t is equal to 0, let's take our first projection, and the particle is over here. How do you take the projection? It just means shadow, right? So shine light from here, we'll take the projection on x-axis. Okay, you can take on any diameter, but we'll consider this diameter, the one which is along the x-axis. Okay, so let's shine light from here and you'll see the shadow of that object over here, right? This is the shadow at t is equal to 0. Now after some time t, suppose 1 second, 2 seconds, sometime t, suppose the particle reaches over here. Okay, I'm just joining this line from the center, it doesn't mean anything. Suppose after time t, the particle reaches over here. Suppose this is p1, this is the position 1. Now the particle has reached P2. Okay, it's moving in this direction. Now this is after some time t. Okay, now again let's take the projection. So we'll say this is P1. Again we'll take the projection over here. We will shine light from here, right, perpendicular to the screen. Screen is the x-axis. Okay, so perpendicular to the screen, and you'll have the shadow somewhere over here. Okay, let's drop a perpendicular from there. Okay, so somewhere over here. Okay, so this is the position P2. Okay, now again after some time the object will reach over here. Again, now we are just supposed to repeat this procedure and see what the projection, what the shadow of uniform circular motion is doing. Okay, so we are supposed to do that. Now this is P3, right? This is the third position. Now when you shine the light perpendicular to this, you'll see that the shadow and your projection and the particle will almost overlap, right? It's over here, it's on the screen, and if you shine light over here, the shadow will almost like overlap in a way. Okay, so yeah, we have the shadow over here, right? So far so good. Let's move to the next section. If you see P1, P2, P3, P3 and then okay, so let's come over here. So the particle is moving in uniform circular motion in clockwise direction. Okay, so it goes from P1, P2, P3. Now over here, okay, let's take it somewhere over here. Okay, now again after some time the particle reaches over here. This is position P4 and we are going to shine light on this object, right? So now we'll shine light from here, okay, perpendicular to the screen, but from here, right? So light from here and light from here. So that gives us the projection, right? So P4, let's find the projection of this. So projection basically means shadow. Okay, so P4, if you can see that. Now after some time t, it will reach over here. This will be P5. Let's get the projection of this. Shine light. Here's the shadow. This is P5. Now you can clearly see it's to and fro motion, right? P1, P2, P3, P4, P5. Let's come to this side. Now when the particle reaches P6, you'll see that the projection is at the same point as the beginning. Okay, so particle, suppose it reaches P6, the projection will be again over here. Okay, let's come to the other side now. Now it's P7, right? So again after some time the particle reaches here. This is P7. You shine the light, you see the projection will be somewhere over here, right? The shadow will be somewhere over here, so it is P7. Okay, let's come to P8. Let's consider it over here. Okay, this is position 8. Now you find the position of the projection of the shadow. Okay, shine the light, again same procedure. Okay, so P8 over here, P9 will take it over here. Okay, if you see when the object reaches over here, the shadow and the object will almost overlap, right? It's almost it's at the screen and you shine light on it, you won't see the shadow. If I shine light on my hand, you won't see the shadow, right? So shadow is considered to be over there, okay, exact at the same point. Okay, now let's go to the remaining portion. So you can see P1, P2, P3, P4, P5, P6 again at the same point. Okay, I'll name it as P6 over here. So P6, P7, P8. Okay, and what will happen next? Can you guess it? Okay, the things that is going to happen, the things that are going to happen is P9. Okay, P9 is also found out. Then P10, P11, P12. Okay, so you can see to and fro motion. So the shadow, okay, let's complete it first of all. Okay, no more talks in between. So let's come over here. This is P10. Okay, this is the 10th position. Again, after some time it reaches over here. Now shine light from the top. Okay, this is the screen. Shine light from the top and you'll have the projection somewhere over here. Projection basically means shadow. Okay, so here we have P10. So if after some time the particle reaches over here, P11, get the shadow of that particle and you'll see that it is P11. Okay, so the particle is performing uniform circular motion, right? It's performing uniform circular motion in clockwise direction. Okay, good enough. Now if you see, the shadow of that particle is performing to and fro motion, right? P1, P2, P3, P4, P5, P6, P7, P8, P9, P10, P11, P12. P12, again the object will reach over here and the shadow will be over here. Okay, so again let's go through it. So P1 at the mean position, okay, I'm calling out those terms now. P2, P2 over here, where is it? Okay, P2, P3, P4, P5, P6, P6 again at the mean position, P7, P8, P9, P10, P11, P12. Okay, so the particle is moving in uniform circular motion, but the projection, the shadow of that particle is going to and fro. And is this SHM? Now it's not verified, okay, not verified, but we can see to and fro motion. All to and fro motions are not SHM. If you know, you know, okay. So we have to verify that this to and fro motion is SHM. And we will verify that this to and fro motion is nothing but SHM. Okay, we'll do that in a while, but before that I just want you to appreciate that this is not something discrete. Okay, it's not like P1, P2, P3, P4, P5. It's something very continuous. Okay, now this happened because we looked at it at specific moments, right? This is at t is equal to 0, after some time t, after some time, after some time, after some time, right? What if we had to look at it in a continuous manner? Okay, we just watch it. Okay, in that case you'll see the shadow going to and fro in a continuous manner. Don't believe me? Suppose it starts at P1 at time t is equal to 0. Now you are watching at it continuously. Okay, so it has reached over here, shadow is over here, shadow over here, shadow over here, shadow over here. So you can appreciate that if you look at that apparatus, whatever we are doing in a continuous fashion, the diagram will complete itself, right? You'll see the shadow going to and fro, back and at the same position. Okay, so this is not something discrete. The particle, the projection, the shadow is not jumping P1, P2, P3. It is going to that position. It's moving. Okay, so it starts from P1, it goes to P2, P3, P4, P5, back to P6, P7, P8, P9, P10, again back to. Okay, so the to and fro motion, it's not jumping steps, it's happening. Okay, so that is something that I want you to appreciate. Anyways, in the next module, I can say we'll discuss the derivation, will prove that this to and fro motion is nothing but SHM, and maybe that is how these two are related. Okay, so over to the next section or module. So our second objective is to prove that the to and fro motion of the projection, the to and fro motion of the shadow of uniform circular motion is nothing but SHM. Okay, and that is how these two are related. Okay, so let's prove that. You can treat this as a derivation. Before that, I told you that if a particle, if a motion is SHM, then it has to satisfy some equations, right? The force is of the form minus kx. So here we need to prove that the force on this shadow is of the form minus kx, okay, which is difficult to prove. Again, we can prove that the acceleration of the shadow is minus omega square x, which is again a difficult task. So we'll do it by the simplest way. We'll just prove that this shadow is following the equation of SHM, okay, the general equation which says x equals a sine omega t plus phi, or x equals a cos omega t plus phi, which are the general equations of your SHM. Okay, so let's see. So you can treat it as a derivation. It is a derivation. We are proving that to and fro motion of the shadow is nothing but SHM. Okay, so let me tell you what's happening over here. Here we have a particle which is moving in a uniform circular motion. Okay, the particle is at a position P at time t is equal to 0. Okay, so it is at a position P at t is equal to 0. Okay, and it's making an angle phi with respect to the positive y-axis. Okay, it's making an angle phi. Now, since it's moving in your uniform circular motion, it will sweep an angle theta after time t. Okay, suppose it sweeps out an angle theta after time t. Time t can be any value, 1 second, 2 second, 3 second. Okay, so after time t, it sweeps out some angle, right? The particle is moving. So you can write this theta, this angle swept, as omega into t, right? Because this is angular displacement, angular velocity into time. Angular displacement is equal to angular velocity into time. Just like distance is equal to speed into time, angular analogues. Okay, so you can write this theta as omega into t. Omega is the angular velocity, and in this case, since it's uniform circular motion, it's constant. Okay, so anyways, that was a addition point over there. Okay, so let's come back over here. Now what will we do? Here you can see that at time t we have taken the projection of this particle. Okay, projection, the shadow of this particle, you see it over here at p dash, right? And the distance of that shadow from point O is taken as x. Okay, now point O is nothing but the mean position, if you can see, right? If this was SHM, this would have been the mean position. Okay, it is SHM, we are proving that. And this distance is nothing but, now I know it's the radius, let's name it r. Okay, OR is nothing but the radius, but it is also the amplitude. Okay, so OR is the radius and also the amplitude of your SHM, which is equal to amplitude. Okay, because if you see, OR is the maximum displacement that your shadow can have. If you remember the P3 position was over here, shadow and the particle overlapping, right? And that is the maximum displacement. It goes to the maximum displacement and then comes back, right? So this is the maximum displacement or just the amplitude of your SHM. Okay, so we'll take the radius of this circle as A. Okay, the radius of this circle as A, which will be the amplitude of our SHM. Keep that point in mind. The radius of the circle is nothing but the amplitude of SHM. Okay, so these two things we have established. Now we are going to look at this triangle. Okay, I'm just dropping a perpendicular from point P dash on the y-axis. Okay, so let's focus on this triangle. I'll take it out over here. So AOP dash. Okay, so triangle is somewhat like this. This angle is phi plus theta, right? AOP dash. So this angle is phi plus theta. Phi plus theta. Okay, and this side will be nothing but AP dash will be nothing but equal to x, right? This is a rectangle. This is a rectangle, right? So this side and this side will be equal, so it will be equal to x. Okay, this distance is x, right? OP dash, we have chosen it as x. Okay, remember that x is the displacement of the shadow. Okay, displacement of the shadow from the mean position. Okay, so your AP dash, we can write it as x, opposite sides of your rectangle. And now OP dash is the radius of the circle or the amplitude. Okay, or the amplitude of SHM. Okay, now you can write sine theta from here, sine of this angle. Okay, sine of phi plus theta, or I'll write theta plus phi equals x by a. Okay, sine of this angle opposite upon hypotenuse, and you can write it in a better format, and you can see the equation of SHM over here. Okay, the displacement of the shadow is given as a sine omega t. Now theta can be written as omega t plus phi, which means that your shadow is performing SHM. The to and fro motions that the shadow was performing was nothing but simple harmonic motion. Okay, so this is the proof for it. This is the derivation for it, that the to and fro motions of the shadow was nothing but SHM. Okay, we'll dive into the numerical aspect. Just a small line that I want to say. Okay, this is often given in your books, so we'll frame it here as well. Okay, so we'll say that your uniform circular motion, the projection of uniform circular motion, okay, the line goes this way, the projection of uniform circular motion on any diameter. Now we specifically chose our x-axis, right? We chose this diameter, but it is true in any diameter. You choose any diameter, you just shine the light perpendicular to it and you watch the motion of the shadow. Okay, that will be simple harmonic. So I'm framing it, what was I saying, the projection of uniform circular motion on any diameter is SHM. The projection of uniform circular motion on any diameter is SHM, or look at it this way, okay? So SHM is not SHM. SHM is the projection, is the shadow of uniform circular motion. Nice, right? SHM is not SHM. SHM is just the shadow of uniform circular motion. And we are studying it as a whole different chapter. It was just the shadow of uniform circular motion, right? So to put that in a better way, SHM is just the projection of uniform circular motion along any diameter, okay? So this is the proof for it. So the way they are related is that the shadow of your uniform circular motion is performing SHM. So that is the way they are related. Uniform circular motion is itself not SHM, but its shadow is, okay? So let's move to the third aspect of the story, the third section of the story, which is the numerical approach, okay? I'll tell you how to approach the numericals, and then we'll dive into lot of numericals, okay? That is the fourth part. Third part is the approach, okay? So let's move to the approach section now. Part 3 of the story, which is the numerical approach. Now numerical approach is no big deal. You are just supposed to follow 3 simple steps, and boom, you'll have your answer to every question which is based on this concept. Now this is a standard approach. I'll provide one more approach to you when we are doing the questions, okay? When we dive into the part 4, okay, I'll give you one more approach. That approach gives you answer within a go, okay? Answer within one step, okay? This is a bit lengthy, not that much, just a bit lengthy as compared to that, okay? So yeah, so the 3 steps that here you are supposed to follow are, first is to choose the clockwise direction, okay? So if you have the freedom to choose the direction of your uniform circular motion, then choose the clockwise direction, because we considered this in our derivation, and yeah, we know the concept from this point of view, right? We'll also discuss the anti-clockwise case. Don't worry about that. It is not absolutely necessary. Only if you have the freedom to choose the direction of your uniform circular motion, choose the clockwise direction, okay? The second step is to write the equation of SHM, okay? Write equation as x equals a sine omega t plus phi, okay? This was the thing that we derived. Okay, so the second step is to write the equation of the particle. Now, here phi is to be measured. So phi is the phase angle, right? So phase angle, the initial phase angle, phi is to be measured from positive x-axis, is to be measured from, if you can remember the derivation, okay, phi is to be measured from positive y-axis. Okay, so suppose if you have the particle over here, phi is measured from the positive x-axis to that point, okay? This is phi. Suppose you have the particle over here, okay? Phi should be measured from the, now suppose if you have the particle over here, now you'll measure phi from the positive x-axis, sorry, positive y-axis, right? This is the positive y-axis to this point, right? This is the angle phi. If you have the particle over here, okay, phi will be from the positive y-axis to that point, okay? So this is the way you are supposed to measure phi, okay? And they'll simply ask you for the equation of the particle in the numericals, okay? So the 3 simple steps are: choose the clockwise direction if it's available. Second is to write the equation x equals a sine omega t plus phi. Phi is to be measured from the positive y-axis. These are the 3 simple steps which if you follow, you'll get the answers in within some seconds, okay? So let's move to a lot of numericals now, okay? Question 1 over here, it's numerical times. So here you are supposed to find the equation of SHM. Here you are given a particle which is performing uniform circular motion, as you can see, okay? So find the equation of SHM performed by its projection, okay? So the projection of this particle will perform SHM, right? So you are supposed to find the equation of SHM. Okay, what were the three simple steps? First, clockwise direction. It's already in the clockwise direction, no fear over here. The second step is to write x equals a sine omega t plus phi. Okay, omega t plus phi. Now phi is to be measured from the, now in each of the problems these values will be given. The value of omega will be given, a will be given, so you are just supposed to substitute this. Okay, now our point is to substitute phi, right? Other things are not given over here. A will be equal to the radius of the circle, if you remember. Okay, so and omega is also not given, so let's keep them as variables. We know something about phi over here. Is this phi? Is 30 degrees phi? No, phi is to be measured from the positive y-axis. So phi is this angle, and this angle will be 60 degree, right? This total is 90, this is 30, so this will be 60, right? So this is 60. So the equation becomes x equals a sine omega t plus 60. Okay, I'll tell you one more approach in the next question. Here you will not appreciate it that much because here the answer came in one step. Further you'll see that answers take a bit of more steps. Okay, so there you'll appreciate that approach, and that approach is special. Okay, it gives you answers in one shot, one go and one step. Okay, let's move to numerical number 2. So question 2 over here, you can try it yourself, discover the joy of doing it yourself. Okay, so here we have a particle P which is performing uniform circular motion. The question remains the same. Find the equation of SHM performed by the projection of this particle. Okay, so first of all, it is already in the clockwise direction, as you can see, right? So need not worry about that. Let's go to the second step, which is writing the equation, right? Here we'll discover the second approach. Okay, and I bet you are going to love it. Okay, so first let's do it by the standard approach, which is x equals a sine omega t plus phi. Okay, so now a is not provided, omega is also not provided in the question, so we'll keep them as variables and we'll substitute phi, right? That is what the question wants us to substitute. Okay, so what is the value of phi? Now phi is measured from the positive y-axis, right? So phi is from positive y-axis till this point, right? Phi is this angle. Okay, so you can see that it is 180 minus 30, or you can see it is 90 plus this angle is 60, right? So 90 plus 60, or it is 180 minus 30. In either case it is 150, right? So let's write it as 90 plus 60. 90 is pi by 2. Let's write it in radians. Plus 60. 60 we'll write it as pi by 3, right? Now a little bit of math is required over here. So a sine, I'll rearrange it, pi by 2 plus omega t plus pi by 3. Okay, I rearranged this. So you can see the format sine pi by 2 plus theta, sine pi by 2 plus theta. Now if you know sine pi by 2 plus theta, multiple of pi by 2 or pi by 2, the ratio will change, it will become cos, and it will be cos theta, right? Sine pi by 2 plus theta in the second quadrant, right? Pi by 2 plus theta somewhere in the second quadrant. So in the second quadrant sine is positive, so sine, the ratio will change because it is pi by 2, and here you'll have cos theta, right? Sine pi by 2 plus theta, this is theta, so it is sine pi by 2 plus theta is cos theta. A little bit of math is required over here. If you don't like the math approach, I have one more approach for you. Okay, but follow it up. Okay, follow it up. It will be little bit confusing because you are supposed to balance the two approaches, right? So yeah, follow it up. Okay, so the second approach, this approach will give you the answer within one step. Okay, you'll get to this point within one step. You don't need to do all these calculations. Okay, so if you are a BITSAT student or a NEET student who doesn't like doing math or doing the steps, BITSAT people, right? So those people can follow the approach that I'm giving now. Okay, the approach is you are supposed to start over here, the particle is over here, right, at t is equal to 0. You are supposed to go back, go back, go back, go back, go back, go back, go back until you land up on a axis. Go back until you land up on a axis. Step 1, right? So you land up on the axis, you look out for the position. What is this position? In an SHM, it is the extreme position. If you see, this will be the positive extreme, right? This is plus A. This will be minus A. This is the mean position. This is the mean position. This is the positive extreme. Now, what is the equation of SHM which is starting from extreme position? It is x is equal to a cos omega t. At least this much you should know, okay? Okay, I'll sum it up somewhere, okay? So if the particle, now this is for those who don't know about this. Actually, you discussed this in the first class of SHM. But yeah, if you don't know this, let me tell you. If the particle is starting at the mean position, okay, at the mean position, going in the positive direction, then you write x is equal to a sine omega t, right? Those who know this can skip it. If the particle begins at the mean position, goes in the negative direction, you write x is equal to minus a sine omega t, right? If the particle begins at positive extreme, okay, which is in this case, you write x is equal to a cos omega t. Okay, if it begins at positive extreme. Okay, if it begins at negative extreme, you can write x is equal to minus a cos omega t. For those who didn't knew about this earlier, can note it down. Okay, we are going to use this in our second approach. Okay, so let's come back to our second approach. First step was to go back, go back, go back, go back, go back until you land up on the axis. Now look out what point that corresponds to. Okay, that corresponds to positive extreme, right? It is the positive extreme. So for positive extreme, the equation is of the form a cos omega t, right? A cos omega t. Now we know that the particle is not starting from the extreme. It's starting somewhere over here. We went back, right? So we'll write plus phi, which is the initial phase difference. Okay, so it is of the form a cos omega t plus phi, because it is not starting at the extreme, it is somewhat ahead, right? So now, so it will be a cos omega t, and this phi, now there will be confusion, this phi should be measured from this axis. Phi to be measured from the axis on which you land. Okay, phi to be measured from the axis on which you land. So you landed up on this axis by going back, so phi to be measured from that particular axis. So phi to be measured from this axis, so which is 60 degrees. Okay, so if you feel that this approach is a little bit confusing, okay, you can go by the standard approach. I'm not forcing you to apply this approach. Okay, you are supposed to remember this thing, and it gives you an answer within one shot. Okay, but you are supposed to remember this thing. It is in a way confusing with this one, because in this case you measure phi from the positive y-axis, and in this case you are supposed to measure phi from the axis on which you land on. Okay, so it's if it's confusing you, then you can leave this approach. Okay, just follow the conventional approach that we have. It may take time, but it's accurate. Okay, and if it's not confusing you, if you are a pro, then you can go by this method. Okay, so anyways, we'll practice more problems, and I'll try to again and again do the problems from both the approaches, so that it's clear to you. Okay, so don't worry even if it's not clear at this stage. Okay, move on. Okay, so let's move to the next question now. So question 3 over here, again the same story. We have a particle going in uniform circular motion. As shown, you are supposed to find the equation of the projection of this particle. Okay, so let's speed run it. Okay, let's do it by both the approaches. Let's follow the conventional approach first, right? So first thing, it's in the clockwise direction. Yes, no need to worry about that. Next thing, you write x is equal to a sine omega t plus phi. Okay, you can use any one approach. I'll do it by both because I want to make it clear to you. Okay, so x will be Now a is not given, omega is not given, so keep the values as it is, keep them as variables. Just substitute the value of phi. Now phi in this approach should be measured from the positive y-axis, right? So measure it from here, okay? So phi is this whole angle. So pi plus pi by 4, right? This angle is pi. This angle is pi, and here we have pi by 4. So pi plus pi by 4, that will be our phi. Okay, so this is pi plus pi by 4. Now again, I have to rearrange this. Now you can do this rearranging step in your head. I'm just proving my point that this method is lengthy. Okay, so pi plus omega t plus pi by 4. Okay, so you can see that it is of the form a sine pi plus theta, a sine pi plus theta, sine pi plus theta. Sine will remain sine and it will become minus, right? It's in the third quadrant, pi plus theta, somewhere over here in the third quadrant. So it will become minus sine theta. So it is minus a sine theta. Theta is this thing, omega t plus pi by 4, right? Now we could have done this in one step, right? So let's do it by the Cabby method. Okay, so that is x equals a. Now the thing is, we are supposed to go back, right? Go back, go back, go back, go back, go back, go back. Okay, we reach over here. Okay, now look at what this position corresponds to. Look at the shadow. If you look at the shadow, you see that this is the mean position. Mean position, okay, and the particle is going in the negative direction, right? This is the positive direction. Here you have the positive extreme, and this is the negative direction, negative extreme, right? Minus a, here you have plus a. So the particle is starting at the mean position, going in the negative direction. Okay, so what was the equation for that? If you can look back in your notes, okay, it was minus a sine omega t. Now of course the particle is not starting over here, it has some phase difference, right? So minus a sine omega t plus phi. Okay, and in place of that phi, you are just supposed to substitute the phase angle from this axis, right? From this axis. So this phase angle is already given as pi by 4. So minus a sine omega t plus pi by 4. Yeah, so that is what I was saying. This approach gives you the answer in one step, and this is a bit lengthy, but your way of looking at it, okay, you may approach in any way. As far as your answer is correct, I never mind. Okay, so let's move to the next question now. A lot of practice, guys. So question 4 over here, you are supposed to find the equation. Okay, again the same story. Okay, so by the standard approach, the point 1 says it should be in clockwise direction. So oopsie, not in clockwise direction. So what will we do? Okay, let's continue doing it. So as I said, clockwise direction is not a necessity. Okay, even if it's not clockwise, you can consider it. Just for your convenience, you are choosing the clockwise direction. If you have the freedom, choose the clockwise direction. They already gave you anti-clockwise direction in a problem, that then you can also tackle it by using the same approach. Okay, so it is not a necessity. Okay, so you can write x is equal to a sine omega t, completely ignoring the first point. Okay, although it is in the anti-clockwise direction, right? So the thing is, you are supposed to measure phi from the positive y-axis, right? In this approach, you measure phi from the positive y-axis. You can see that it will be, okay, let's write it this way, 270 minus 30, right? 270, this total angle is 270, 90, 90, 90, 270 minus 30. Okay, you can write phi that way. Okay, you can also write pi plus 60, right? This will be 60. So I'm writing it as 270 minus 30. Okay, so just to compare it with the other approach. Okay, so that will be 270 minus 30. Okay, so that we get both the answers same in both the approach. Okay, so you can see that it is, I'll rearrange it, a sine 270 plus omega t minus 30. Okay, so a sine of 270 plus theta. Okay, sine of this is a multiple of 90, 93s are, right? So the ratio will change. It will become cos 270 plus theta, 270 plus theta, that is the fourth quadrant. In fourth quadrant, sine is negative. A little bit of math over here. So minus a sine theta. Okay, theta is omega t minus 30. So sorry, omega t minus 30. Let's do it by the other approach. Okay, what does the other approach says? It says go back, go back, go back. Okay, so go back, go back, go back, go back until you end up over here. If you see, this is the negative extreme, right? This is the, okay, here the ratio will change. Okay, sine 270, right? That is a multiple of pi by 2, so the ratio will change to cos omega t minus 30. Okay, let's come back over here. So you reach this point, right? This is the negative extreme. Negative extreme, how do you write the equation? Minus a cos omega t plus 5. Okay, fine. Okay, so now phi should be measured. So what is phi over here? Phi should be measured from this axis, right? Phi should be measured from the axis on which you land. Okay, so measure it from this axis. It is 30, right? It is 30. So a minus a cos omega t plus 30. No, it will be minus 30 because we didn't uh, take it in the clockwise direction. If you see, it's in the anti-clockwise direction. It was an assumption which we couldn't see. We considered the angles in the clockwise direction. Even in the derivation, you can see that we chose the angles in the clockwise direction to be positive, right? This angle is in the anti-clockwise direction. You are going from this axis to this. Okay, this angle is in the anti-clockwise direction. Since we have considered the angles in the clockwise direction to be positive, angles in the anti-clockwise direction should be negative. Okay, so here the phase difference is minus 30. Okay, remember that. So this is our equation which is in agreement with this, right? So that is one more way of doing it. Okay, that is all what I want to say from this question. So even anti-clockwise, even if you have the uniform circular motion in anti-clockwise direction, you don't have to fear. You can go by any of the approach. Okay, the approaches hold over here. In place of 270 minus 30, you could have also substituted pi plus theta. Although you'll get a different answer, okay, it will be correct. Okay, I just substituted 270 minus 30 because I wanted the answer to be in agreement with this one. Okay, so that is the way you do it. And now let's step up the levels. These were very kiddie questions, I would say. These were straightforward questions. Let's practice some more good questions from which are based on this topic. Okay, so over to the next question. So question 5 over here. Now this type of questions are more likely to appear in your exams rather than the questions that we discussed. Majorly the questions that we discussed previously were majorly for your understanding. Okay, now you'll be able to do this type of questions quicker. Okay, so now let's read this. Particle initially at x equals plus a by 2 is moving in the negative direction. So we have a particle which is performing SHM, right? So it's a SHM question, guys. Okay, so it's moving in the negative x direction and it is initially at plus a by 2. You are supposed to find the equation of this particle. Okay, so what are we going to do? We are going to treat this particle as a shadow of some other particle which is performing uniform circular motion, because we know that SHM is not real, right? SHM is just a projection of uniform circular motion. Okay, SHM is real. I just said that for fun. Okay, so now so initially our particle is over here, right? Plus a by 2. This distance is plus a by 2. Okay, so this is the shadow. We'll treat our particle as shadow, right? So our particle in the circular motion can be over here, right? This particle is the shadow. This is the other particle which is performing uniform circular motion, right? The shadow of this can be over here, or we can have one more point. The shadow of this point can be over here, right? So there are 2 points wherein the shadow can be at plus a by 2. Okay, so which is the point that we want? Okay, now this line is will tell us that moving in the negative direction. Now we'll consider the clockwise direction, because we have the freedom, right, and we know the concept in that way, right? So we'll choose the clockwise direction, and if you see if you choose the clockwise direction, you'll see that this is moving, the shadow in this case is moving in the positive extreme. It is moving towards the positive extreme over here. Here we have plus a, right? So the shadow in this case is moving towards plus a, right? And whereas the shadow in this case is moving towards the negative direction, right? So this is the point where we are starting. Okay, so this is the initial position of the particle. Okay, because it said it's moving in the negative direction, that is moving in the positive direction, so that is wrong. Okay, so let's connect this point now. So we know that this OP will be equal to A, right? The radius of the circle equal to amplitude, remember? So we can find this angle now. Okay, this theta now. Theta can be given as, we'll write cos theta. Cos theta will be adjacent. Adjacent, if you see, it's the distance x. Okay, adjacent. This is the adjacent value. So a by 2 divided by a. So that will give you half. So cos of which angle is half? Cos of 60 degrees is half, right? Cos 60 is half. So this angle is 60 degrees. Okay, so we know this angle, we can replace it by 60 degrees. Okay, now what's the next step? We are supposed to find the equation. Now it's a cakewalk for you. It has boiled down to the same problems that we discussed so far, right? We were just supposed to decode this thing, and now it's the same problem that we were discussing so far, right? So angle is given over here. Here you are also provided some other values. We'll use that in equation. So we'll write x equals a sine omega t plus phi, right? Going by the standard approach. So a value is given as 1. So sine omega t, omega has a formula. It is 2 pi by t. Okay, 2 pi by t, where t is the time period. It is given over here. So 2 pi by time period 2, so that will give us pi. Okay, let's keep it as omega t, then we'll substitute that later. Now plus phi. Phi should be measured from the positive y-axis, right? So you have to measure phi from here. So this plus this. So 90 plus 60, so pi by 2 plus pi by 3, that is sine 90 plus theta. Sine 90 plus theta, that is cos theta, right? Yes, so cos omega t plus pi by 3. Okay, so that is our answer. You can also do it by the other approach. So you'll write x equals, go back, you'll end up on the positive extreme. Positive extreme says a cos omega t plus phi. Phi should be measured from this axis, since you will end up on this axis. So phi is 60 degrees. So 60 degrees is pi by 3, right? Yes. So that is the equation of this particle. Anyways, we are supposed to substitute the value of omega over here. Okay, omega can be written as 2 pi by t. Remember this. This is something very, very basic. So x can be written as cos. In place of omega, you can put 2 pi by t. T has value 2, sorry. So that gives us pi plus pi by 3, right? Pi t. Okay, in place of omega, we substituted 2 pi by 2, that gives us pi. T value is 2 over here, so that gives us pi. So pi t plus pi by 3. So a is 1, right? A is 1. So x equals cos pi t plus pi by 3. Okay, so that is how you do problems of this kind. Okay, one more problem of this kind we'll do, and then we'll level up. Okay, even more level up. Yeah, let's move to the next question. So question 6 over here, just a practice to the previous one. So let's speed run it. So the particle initially is at a position x is equal to minus a by 2 and it is moving in the negative direction. Okay, you are supposed to find the equation of the particle. Okay, so the particle initially is at this position, right? Minus a by 2 in the negative direction. we have a by 2. Okay, this is in the negative direction. This is the negative direction. This is the positive direction. Okay, so now what's the next step? We are supposed to find the two positions of our uniform circular motion. It can be over here, right? So in order for that shadow to be over here, for that shadow to land at minus a by 2, our particle can be over here or here, right? So that when you shine the light, the shadow will end up over here. Okay, so those are the two positions. We are going to choose the clockwise direction. Okay, so this direction, and as you can see now, we can eliminate one of this. Our particle is initially moving in the negative direction. So if you see, this is the correct one, right? This is moving in the negative direction. The shadow of this particle will move in the negative direction. This shadow, the shadow of this particle is moving in the positive direction. This is the wrong one, this is the correct one. If you go on taking the shadow of this object, it will go in the negative direction, here, 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 and it's moving basically towards the negative extreme, right? So now let's write the equation for this. So we are supposed to find the angle now. We want angle, right? At least one angle to find the phase difference over here. So we'll connect this point. We know that this is the radius of the circle. The radius of the circle is nothing but the amplitude. Okay, so it is equal to A. Okay, now we'll find this angle theta, speed run. So cos theta, you can see that it's same as the previous case. It will be 60, right? A by 2 and A, it will give the angle as 60 degree. Okay, you can do that, but the answer is 60 degrees over here. So this angle, we know that it is 60 degrees. Okay, now let's find the equation. Now finding equation is a cakewalk. We can use any approach. First approach says x equals a sine omega t plus phi. So okay, so phi should be measured. Now nothing of the other is mentioned. Okay, so we'll keep them as variables. Plus phi should be measured from the positive y-axis. Remember that. So measure it from here. Okay, so this is pi plus this angle. This angle is 30 degrees, right? So pi plus 30, so 180 plus 30, or pi plus pi by 6, right? 30 is pi by 6. So rearrange that. I can write it as sine pi plus theta, right? Sine pi plus theta. Ratio won't change. That will be in the third quadrant, so it is negative. Okay, so I can write it as minus a sine theta. Theta is omega t plus pi by 6. Okay, you can rearrange and do that. This is the answer that you are supposed to get. Now going by the second approach, the Cabby approach. Okay, it says go back, go back, go back, go back, go back until you land on this axis. So you land on the mean position. If you see the projection over here, the shadow is on the mean position. Mean position moving in the negative direction, right? So you'll write x equals, it's already given over here. So it's starting from the mean position and going in the negative direction. If you are noting it down, it is minus a sine omega t, right? And of course, it does not begin over here. It begins over at some phase difference, right? So it has some phase difference, and that phase difference should be measured from the same axis on which you land. So it should be measured from this axis, and which is, we have written that as 30, right? So pi by 6, minus a sine omega t plus pi by 6. Okay, it's starting from the mean position going in the negative direction, so minus a sine omega t, and it has some initial phase difference plus phi. Phi is 30 degrees over here. Okay, so yeah, that is the answer to our question. Let's level up. Okay, yeah, we have more 2 questions to come, and then we'll wrap up with today's class. Then you are good to go with this concept. Okay, so question 7 over here. In this question, you are asked for the shortest time for the SHM to move from plus a by 2 to minus root 3a by 2. Okay, so find the shortest time for a particle which is performing SHM to move from plus a by 2 to minus root 3a by 2. You have your options over here. T stands for time period. You can give it a try. Okay, so the particle begins at plus a by 2. right? And it goes to minus root 3 a by 2. You can pause the video here, you can try it out for yourself, okay? So plus a by 2, the particle is initially over here, okay? So the particle can start over here or over here, okay? This is the shadow, okay? That is the idea that we are using. So we'll consider the clockwise motion, we know that. And finally the particle should land up at minus root 3 a by 2. Let's consider that somewhere over here. So minus root 3 a by 2 over here, okay? So in the circular motion we can have the particle over here so that its shadow is over here, or the particle can be over here so that its shadow is at the position minus root 3 a by 2, okay? So again clockwise direction, okay? So you can see that you have many paths from a by 2. You actually have two paths, okay? You can begin here and go here, or you can begin here and go here, okay? Which will take the shortest time. That is the thing that you are supposed to see, okay? So if you choose this path, okay, if you begin over here and reach over here, you can see that it will take longer time, right? You can see itself in the circular motion, right? In the circular motion you can see that your particle has to sweep a greater angle, right? It begins over here and it has to reach over here. Particle has to move a greater angle, right? And angular velocity is same, right? Uniform circular motion. If the particle begins over here, it has to just move this angle, right? From here to here. Or if you want to look it into the terms of SHM, here you can see that it's beginning at a by 2, right? And it's moving in the positive direction. It's moving towards the positive extreme if you begin over here, right? So it begins at plus a by 2, it goes to plus a, it comes back to plus a by 2, okay? It comes to a, then comes to 0, the mean position, and then it comes to minus root 3 a by 2. Okay, so that is a long journey if you begin from here. Whereas if you begin over here, okay, the second position a by 2, okay, and it's already moving in the negative direction. That is the advantage. So it moves to the mean position first and then minus root 3 a by 2. So in both ways you can see that the shortest path is from here to here, and that will take the shortest time, right? You can feel it more in the case of uniform circular motion, right? This is greater angle, right? From here to here, your a particle has to sweep a greater angle as compared to from here to here. From here to here, it's a bigger angle than here to here, right? So that idea. So we are just supposed to find the time taken for this journey from here. Now the shortest time we know it will be from here to here, right? So we are supposed to find time for this journey now. From here to here, okay? So in order to find that, we are supposed to find this angle, right? That angle, if we know, we can find, yeah, if we know that angle, we can find the time taken for this journey, okay? So first of all, we can find this angle, okay? If you consider this as O, this as P, you'll see that this will be 60 degree, right? A and A by 2. This is A, right? This is OP is the radius of the circle or the amplitude, okay? So A and A by 2 makes it 60 degree. And similarly, A and minus root 3 A by 2, it will make it 30 degree. Okay, don't believe me. Let's consider this as theta for a second. So cos of theta can be written as root 3 a by 2. I'm just considering the magnitude, okay, divided by a, okay, adjacent upon hypotenuse. So a and a will get cancelled, and cos theta you will get the value as root 3 by 2, which means it is cos 30, right? So theta is 30 degrees, okay, cos 30 root 3 by 2, yeah. So this angle is 30 degrees. So what is this angle now? We want to find this angle, right? When we find this angle, suppose this angle is alpha. I'll tell you how we are doing it. Alpha can be equated to omega into t, right? Angular displacement is equal to angular velocity into time. Angular velocity, you already know the relation, 2 pi by t right, and into t. This t stands for time period. This t stands for time taken to move from here to here. Okay, cleared? Now, what is this angle? What is that angle? That angle is, if you see this total is 180, this will be 90, right? This is 180 from here to here. This is a semicircle. It is pi. This is, or 180, and you have to subtract this angle from here and this angle. So minus 60 minus 30. So 180 minus 90, that is 90. So this angle over here is 90, or you can write it as pi by 2. Okay, substitute in radians because here you have substituted 2 pi. Okay, so pi and pi will get cancelled, and you can easily see that the time taken for this journey, right, the time taken, which is small t, is 1/4 of the time period. Okay, t by 4, t by 4. So option C, t by 4, is the correct choice over here. Okay, I hope the approach was clear. Okay, first we found out the possible uh, positions of the particle, then we ignored the ones that couldn't be the right ones. So then we followed the same approach. Okay, followed the same approach for this. From, we can consider this as p q r. Okay, so p to r, you have to move from p to r. What is the angular displacement? Angular displacement is equal to angular velocity into time. Okay, first of all, before that we found out 60, this angle is 60 degrees, this is 30, so that we can calculate this angle alpha. Okay, so that was the simple approach of doing this problem. Let's move to the last question for the day. I hope this was not too much for you. Okay, so let's move to the next one. So question 8 over here, this is the last question for the day, and I think it is also a JEE question. Okay, so let's do it. You can try it out for yourself. Okay, so in this question you are given that the time taken for a particle which is executing SHM to move from 0 to plus a by 2 is Ta, and the time taken for the same particle to move from plus a by 2 to plus a is Tb. Okay, you are supposed to find the relation between the two. Okay, so now some of you might be tempted to say that Ta is equal to Tb, because if you see the displacement in both the cases is equal, right? Here you have to move a distance of a by 2. Here also you have to move the distance of a minus a by 2, which is also equal to a by 2. Okay, so distance in both the case, which needs to be the distance in the journey, is equal, right? So you might say that the time will also be equal. Not necessarily, because if you see, velocity is changing, right? A velocity of an SHM is constantly changing, right? At the mean position it's the maximum, and at the extreme position it's 0. So velocity is going on decreasing. In fact, it will take higher time to cover the second distance, because velocity goes on decreasing, right? So it will take more time. Tb will be bigger than Ta. Of course, Ta not equal to Tb. Tb will be bigger than Ta. Okay, it can be 4 times. Tb can be 2 times. Okay, B and C can be the correct one. D can also be the correct one. Okay, they cannot be equal. Okay, so that is the idea. Now let's do it. Let's actually do it and see. Okay, so the particle moves from 0 to plus a by 2. Okay, so plus a by 2 will be somewhere over here. Let's consider the clockwise motion. Okay, so it goes from 0 to plus a by 2 and then plus a by 2 to a. Okay, so it's over here, not over here, it's over here. Okay, so 0 to a by 2 and then to plus a. Okay, so let's draw this. Okay, so this distance is a by 2, right? And this is the radius or the amplitude of SHM. Okay, and the angle between them will be 60 degrees, a and a by 2. If you can see a and a by 2 from the previous problems, this is something that you can take away. So from the previous problem, it will be 60 degrees. Basically cos of 60 is half, right? So if you treat that angle as theta, cos theta will be a by 2 by a. So that is half. Cos of what angle? Which angle is half? Cos of 60 is half. So this angle is 60 degrees. So this angle naturally will become 30 degrees, right? So 30 plus 60, 90. Okay. Now you can see that for the particle to move from 0 to a by 2, right? For the particle to move from 0 to a by 2, your circular motion, in circular motion, it just means to move an angle of 30 degree. Okay. And for the particle to move from a by 2 to a, it means to move an angle of 60 degrees. Why is this so? Okay, this is something that you'll tell me in the comment section. Majorly because I told you about it. It's because the velocity is decreasing, right? So that's the main reason over here. Okay, so looking it from the circular motion point of view, you can easily see that the time taken for the second journey will be 2 times of the time taken for the first journey, because angle is doubled, right? So your time will also double because angular velocity is constant. Okay, not getting this? So this is the correct relation. I'll explain you why. Okay, so let's do it. Okay, so in first case we can write omega into ta, right? The angular velocity into time taken is equal to the angle swept, right? So that is 30 degrees, which is pi by 6, right? Correct? Okay. And in the second case, we can write omega into tb. Now omega is the same, right? Uniform circular motion. Okay. So omega into tb is equal to 60 degrees. In the second case, it has to sweep an angle of 60 degrees. Okay. So now 60 degrees is pi by 3. You can take the ratio of this two, or you can simply write this as 60, this as 30. Okay. So you can take the ratio of this two. So Ta by Tb, okay, Ta by Tb, this two you can divide, will be equal to half. So this implies that 2 of Ta is equal to Tb, which is the relation that we want. Okay, so and this is true for any SHM, right? We didn't speak of one particular SHM of amplitude this and that. Okay, we spoke it in a general way. This is true for any SHM. The time taken for half the journey, for the first half of the journey is okay, I'll frame it. Okay, I'll say that the time taken for the second half of the journey from plus a by 2 to plus a is equal to 2 times the time taken for the first half of the journey, which is from 0 to a by 2. Isn't that amazing? And that is a consequence of your velocity, right? Velocity is constantly decreasing in your SHM, or you can see it in the form of circular motion. Here you have to just move an angle of 30 degree to reach a by 2, but you have to move an angle of 60 degrees to reach from a by 2 to a, right? So that was it. Okay, so that's pretty much it for today's class. If you did enjoy it, if it did clear your doubts, if it made you feel confident in this topic, then smash like and also consider subscribing. Okay, and if you have some more topics on which you find confusing, do let me know those in the comment section. Okay, I'll see you soon in the next class. Till then, keep enjoying physics.